this question we're given h of x, and then we're asked to find the local max and min of h using the second derivative test, and then to make a sketch of the graph. So for the second derivative test, what we want to do first is find the first derivative, set that equal to 0 so we can find out where the slope is actually equal to 0 to figure out, where we have either a max or a min, and then use the second derivative to figure out whether or not it's concave up or concave down. And that'll tell us whether or not we're dealing with a local maximum or a local minimum. Okay, so let's find the first derivative of h of x. So we'll go h prime of x is equal to, so this would become 3x squared minus 18x plus 24. All right, so now from there, we'd like to set this equal to 0, right? Because we want to say, okay, where is the derivative equal to 0? So there may be more than one point here, so we're going to factor this. So I see that 3 is common to all of these, so I'm going to factor a 3 out. So we have 3, and then we're left with x squared minus 6x plus 8. All right, so from there, we'll just factor it again. So now we have 3, and this becomes x minus 4 and x minus 2. Okay, so from there, we can see, well, our solutions then, our actual answers for x here, would be x is equal to 4 and x is equal to 2. All right, so these are the places on my graph that I know that the slope is equal to 0. So these are like the horizontal lines you can picture, right? All right, so then from there, these are our, let's make sure we label that too. These are our critical numbers. Okay, so critical numbers are at x is equal to 4 and x is equal to 2. Okay, so now let's find the second derivative. So h double prime of x is equal to, so now we're just going to take the derivative of the second derivative. So that becomes, so bringing the 2 down, we get 6x minus 18. All right, so now all that's left to do is actually just sub in our values, right? Because if I sub in h double prime of 4, and it comes out positive, it's concave up. If it comes out negative, it's concave down. So let's do that now. So we'll say h double prime of 4. If I plug that in, that's 6 times 4 minus 18. So h double prime of 4 is equal to 6. Now, the magnitude of the number I'm not actually that concerned with. The biggest thing here is that h double prime of 4 ended up being greater than 0, right? And that's telling me, so it's greater than 0, therefore it's concave up, right? Because if it's positive, it's concave up. All right, so now let's try the next one. So now you're probably guessing it's going to be concave down, and you're probably going to be right. So if we look at our next one, so h double prime of 2. So if we plug in 2 this time, we get 6 times 2 minus 18. So h double prime of 2 is negative 6. Okay, so this means that h double prime of 2 is less than 0. Therefore, we're going to be concave down. Okay, so, well, maybe while we're at this point too, let's just kind of look back at these. So if this was the case that we were concave up when it was 4, then what does that mean? So if it's concave up, then that must be a local min. Okay, so maybe I'll write that now. Local min. And on the other side of this, if it's concave down and it was a slope of 0 there, then this must be a local max. That has to be the case, right? Okay, so now the next step here is, well, we want to sketch this. So it's good that I found out the x value where these things occur, right? But then what I'm going to have to do is I'm going to have to figure out what the y value is too, because I'd actually like to know the points that I have a local min or a local max. So from here, we're just actually going to go back to the original function and sub in our critical numbers, right, to figure out where those points actually are. Okay, so from there, we'll say, I'll write that down here, h of 4. Okay, well, that would be 4 cubed minus 9 times 4 squared plus 24 times 4 minus 10 I just have the answer offhand, but you could plug this all into your calculator. So this would be 6. So h of 4 is equal to 6. So it would be, or you can think about this as being at the point 4 comma 6 on our graph. Okay, so then this would be our, if we just remember, that was a local min. So this was at a local minimum, just so we don't forget what we're looking at. Okay, and then h of 2, if we plug that back into the original, yeah, I could plug it up. Are you okay if I just say 10? That's what it all comes out. If we throw 2 into our original, it just comes out as 10. So in this case, then, this is really the point, 2 comma 10, and this would be our local max that we found, right? Because that was happening at 2. All right, so now I think we have enough info that we could just make a quick sketch of this. So let's plot our 2 points here. So I'll do 2 comma 10 first. So say, over 2, up 10. I'll make it somewhere up there. So this would be the point 2 comma 10. And then another one at 4, 6. So if I go twice as far as that, and then approximately here, this would be 4, 6. Okay. Now, the other one that might be helpful that we probably should make our graph go through, especially because it's so easy, is that we know that our function actually goes through -10 as well, right? That's the y-intercept of our graph. So I can also tell that this graph should be going through, all the way down here. Okay, about the same distance from the top to the bottom there. All right, so this would be 0 comma -10, right? And then just the best we can, we're going to just freehand this from here. And it's always hard on my computer, but I'm going to try my best. And then something like that. That was actually better than I was expecting. All right, so that would be good enough for our sketch.